Hey people, this is the file for the answers of diagnostic topic test number 4. That's not particularly dynamic. Anyway, question 1. This is the figure from question 1 and that's the circuit from question 1. So you need to use this. It says, shows the voltage versus current graph for two electrical components. And the first question says, by examining the voltage versus current graph, determine which of the two electrical components, P or Q, is ohmic. Well, that one's ohmic. Right. Something that's ohmic adheres to Ohm's law, which is V equals IR. In other words, R equals V divided by I. Right? And the R is the constant here. Anything that's got a constant resistance, no matter how much voltage, no matter how much current is going through it, is ohmic. Right? And graphically, if a voltage versus current graph yields a straight line, that just tells you that the gradient R, right, rise over the run, is constant. So that's an ohmic device. Q is ohmic and P is not. All right. Part B. Excuse me. Part B, it says two electrical components, P and Q, the ones on the graph, are hooked up like this in series, right? Powered by a variable DC voltage supply. That little arrow just means the voltage can be varied, right? So it's got a knob on it that goes 2, 4, 6, 8, and you can choose different voltages, right? Determine the current through component number Q. Excuse me. It says the current through P is 2 amps. Well, it's a series circuit. So if 2 amps is going through there, 2 amps is going through there, right? And this is why this is only worth 1 mark. The current is 2 amps through Q, right? Easy. 2 amps goes through P, the same 2 amps has to go through Q. Part C, determine the potential difference across component P. Now use the graph for this. You now know that there's 2 amps going through both, right? So when there's 2 amps, this is the amps, when 2 amps is going through P, the voltage across it is 5 volts, right? When 2 amps is going through Q, the voltage across it is 2.5 volts. And that's the answers to C and D, right? C and D basically say how much potential differences across each of them, right? 5 volts for C, 2.5 volts for D. You just get it off the graph, right? Part E, determine the voltage supplied by the variable DC voltage source. Well, if there's 5 volts, sorry, did I do this around the wrong way? Nope, good. 5 volts there and 2.5 volts there, right? If 5 volts is being lost between those 2 points and 2.5 is being lost between those 2 points, then the total voltage loss is 7.5 volts, right? There's nothing else on the circuit that can take voltage away. So if 7.5 volts is being used, 7.5 volts must be being supplied, right? So the answer to question E is just you add them together. Whoops. You add them together on camera, Mark. There you go. So that's part E. This is a reasonably quick question to do. Part F, calculate the electrical power supplied by the DC voltage source. Okay, power, F. Power is VI, and now you've got the V and the I for this. And again, keep in mind that the V and the I have to be for the same thing. They have to be for the same area. So the total voltage supplied times the total current supplied, and that's 15 watts. Power is in watts. That's F. Now G, it says the electrical components P and Q are now placed in a parallel circuit. And the variable DC voltage source is 5 volts. Determine the current through component P. Well, let's just get this out of the way for a second. All right. So now they're like this. That's P, that's Q. Okay. And it says the DC voltage source is 5 volts. So it's changed to 5 volts. It was producing 7.5, now it's producing 5. All right. Now keep in mind we still have the graph that we can use for this if we need it, because that'll tell us how much current is going through something if we know the voltage across it. So we'll get onto that in a minute. Right. And it says determine the current through component P. Okay. Well, we know the voltage across P has to be 5 because the electrons that are coming out here are going to take that, or the ones that take that circuit instead of taking this circuit, have got 5 volts and they're only going to use it on P. So we know that for P, the voltage across it is 5 volts. Pardon me. And we can use the graph to figure out what the current must be. Okay, so the voltage across it is 5 volts. The current through it must be 2 amps. Right, there's P. Therefore, I is 2 amps. And if you need some explanation, you just have to say from graph. And that is enough explanation for an examiner to understand that you got it from the graph. You don't have to describe exactly what you did on the graph because you couldn't possibly fluke the answer if you didn't know what you were doing. Right? You wouldn't have guessed that it was 2 and somehow just got it right. All right, determine the current through component Q. Same thing, use the graph. There's component Q, it's just a different line, doing the same thing. If the voltage across Q is 5, and it will be, right, because the voltage across both of them will be 5. So there's 5, we're going to go across to Q's line now. Pardon me, I'll just get this in front of you. 5 go all the way across to Q and it hits there, and the current going through Q must be 4 amps. Right? So they're the answers to G and H. That was G. My setting out is terrible at the moment. Sorry, that is H. I was 4 amps, again, from the graph. All right. One more, I think, in this question. Yeah. Part I, calculate the electrical power supplied by the variable DC voltage force here. So this is part I. Again, power equals V times I, and it has to be supplied, right? So the voltage is 5, but what's the I? Right. Here's the I. We've just found out that 2 amps goes through there and 4 amps goes through there, and when they get back together, they're going to add up. Right? There's 2 and 4, 4 amps of power coming around here, 2 coming around there, so by the time they get through here, it's back to 6 amps. Right? For 2 amps to go that way and 4 to go that way, there must have been 6 at the beginning. They split up to go through the 2 lanes and then they get back together and there's 6 amps. So that is a 6, which means the power is 30 watts this time. More power available if you connect things in parallel than there is if you connect things in series. All right, that's question 1. Question 2, voltage divider circuit. All right. Now there's a voltage divider circuit that says V in is 18 volts and V out is 5 volts. Now that just means that they've got a power source here. They just haven't drawn it. So the rest of the circuit would look something like this. And that's 18 volts. All right? It really doesn't matter how they've made 18 volts, but between there and there, the difference is 18 volts. And V out has to be 5 volts. So if you've got a voltmeter, right? Voltmeter, that's the symbol for a voltmeter, and touched it there and touched it there, you'd get a reading of 5 volts. So this one must be sucking off the other 13 volts, right? That is, siphoning out the rest of the energy. Okay. So how do you answer this? Well, this is actually a proportion question. If the voltage across that resistor is 5 volts and the voltage across this one is 13 volts, then the ratio of the resistances must also be 13 to 5. Right? If that takes more energy, it must have more resistance. If it takes twice as much energy, it'll have twice as much resistance because they're both getting the same current. Right? So they're getting the same current. If their resistances are different, the voltage being different is the only reason for it. So the ratio of R1 to R2 must be 13 to 5. Right? So this is what you do. This is how you say it. R1 to R2 is 13 to 5. And they've told you the value of one of them. They've told you that R1 is 26,000. All right. So therefore, let's just slide this across a little bit. So therefore, 26,000 to R2 equals 13 to 5. So you basically just have to find out what that comes to. Right? That's obviously got to be 5/13 of 26,000. Okay. 5/13 of 26,000 equals 10,000. Right. So it's a 10k ohm resistor. That's the working you need to put into it. Have a look at it, excuse me, have a look at it in the marking scheme that I gave you as well. They pretty much do the same thing. Question 3 doesn't really need me to show you a calculation because there isn't a calculation. This is about explaining something. They've given you a table there that shows you the effect on your body of a certain current of an electric shock. And the important part of the table is that 20 milliamps, which is a pretty small current, it's 20 thousandths of 1 amp. 20 milliamps is enough current for your muscles to be paralyzed. So if you grab a wire, right, if this is a wire and you grab it, right, and it's got 20 milliamps of current going through it and some of it goes into your body, you won't be able to open your hand, even though you might want to, because your hand works on electricity and it works on less than 20 milliamps of electricity. So the power going through the wire is going to stop you from letting go, and you'll have no option but to sit there and be electrocuted. And if it's 200 milliamps, that's likely to kill you. If 200 milliamps goes through your body, if it goes up your arm and out the other arm or out one of your legs or whatever, goes through your torso, that's probably going to give you a heart attack or burn your nerves or do enough damage to pretty much kill you. All right, so question says, explain why a current of 20 milliamps is so dangerous for yourself and other members of your family. This is the important bit you have to answer in your answer. And other members of your family who are in the room and can see that you're being electrocuted. The natural response for somebody who sees someone else, especially someone they love, being electrocuted is to go over to them and try to pull them away from the source of the electrocution. But if I grabbed you while you're grabbing this and you're unable to let go, then I'm going to get that 20 milliamps through me as well, because your body is conducting electricity. So you're still not going to be able to let go of the wire, and I'm not going to be able to let go of you. So instead of you dying, we both die, right? The problem with 20 milliamps or more is that people can't let go. So if I touch you, I'm just adding myself to the circuit, right? The only way I can safely deal with it is to either touch you with something that doesn't conduct electricity, and that's still a bit of a risk, or better still, just turn the electricity off, right? Go to whatever the source is. If you're touching a toaster or something, switch the toaster off, pull the plug out, and everything will be hopefully fine. Call an ambulance. All right. But the short answer to the question is that 20 milliamps, if it's touched by anybody, even via a person's body, will render anyone who's trying to help also unable to move their own muscles. Question 4, an LDR, a light-dependent resistor. So here's a resistor that can change its resistance depending on how bright a light is shining on it. Right? So they can pick up whether it's light or dark and change the amount of electricity going through, right? And change how much resistance there is to it. And we can use that as a sort of automatic switch. If we turn the lights on, it lets electricity through, or some of them work backwards like this one. Whereas if you turn the lights off, it lets electricity through. Let's have a look at this. Is this a forwards one or a backwards one? When there is not much light, this is lux. Again, you're given a graph, get to know the graph before you worry about anything else, right? That's lux. This is how bright a light is that's shining on the resistor. This is resistance. So the brighter the light is, the less resistance this thing has, right? It's going downhill. It's an inverse proportional relationship. So you shine a light on that and it lets lots of electricity through because suddenly it doesn't have any resistance, right? If the lights go out, suddenly electricity has trouble getting through because the resistance is like 10 million ohms. Have a look at that. That's in thousands of ohms. 10,000 thousandths is 10 million ohms. Nothing's getting through that thing. 10 million ohms. It's like a piece of rubber. All right. So this is a device where light shines on it, it lets electricity through. Light doesn't shine on it, it doesn't let electricity through. Okay, sorted that out. Let's have a look at the figures that we've been given here. It's put in this circuit here. The voltage across DE is bigger, or when the voltage across DE, this bit, is bigger than 8 volts, security lights are going to turn on. Okay, so when this thing has enough resistance so that the voltage is 8 volts across there, pardon me, that will trigger some other part of the circuit to turn some lights on, right? Because it's night. This is how automatic street lights work. Nobody drives down the roads turning on the power poles. They go on by themselves because of one of these things, right? And the voltage across DF, the whole thing, not EF, DF, is 12 volts. So straight away, you know that the voltage across this has to be 4 volts because the total is 12, they're in series. All right, so what's the question? Right, it says calculate the value of that resistor, R, so that when the external light goes down to a value of 1 lux, we'll get onto that in a second, the security lights turn on. Right, so what we need is this to exist, right? For DE's voltage to be crossing the 8-volt mark at 1 lux. Okay, so let's have a look at this. 1 lux on this, there's 1. That corresponds to a resistance of 100,000 ohms. Okay, so that's this one. So when there's 1 lux of light shining on this, it has a resistance of 100,000 ohms. And that has to be 8 volts, and that has to be 4 volts, right? Excuse me. So again, this is a bit of a proportion thing. If this resistor is taking 8 volts, and it's 100,000 ohms, and this resistor only takes half as many volts, half as much energy off the electricity supply, then this must be only half the resistance of that, right? So if that's 100,000 ohms, this is 50,000 ohms. Now you can explain that just by writing those 2 sentences if you want. You can set it up like that, like the previous question, like question 2 with that 13 to 5. Either way, either way is fine as far as explanation is concerned. I would prefer to actually write it out, but if you're more mathematical, that's fine. You can just do a ratio thing. You can say 8 to 4 equals 100,000 to x and find x, and it'll be 50,000. All right, so that's the answer to that question. This question was hard because it threw a few things at you that you hadn't heard of before, LDRs and a circuit with this sort of symbol and all of these sort of things, right? It's trying to fool you, but it's a reasonably simple question. Like I keep saying, part of the skill is understanding what they're asking you for. Question 5 is pretty easy if you read the right page in the book. It says describe the energy transformations that occur in LEDs and photodiodes. An LED is a light emitting diode. When electricity goes through it, it glows, right? It's a little tiny light. Right? It's a light that most car indicators are made of now, those little sort of spotlights, those little tiny point lights, aren't they? LEDs. Right? So a light emitting diode takes in electricity and turns it into light. That's the energy transformation that happens into it. Right? A photodiode is the exact opposite. A photodiode makes electricity go through it when light is shined on it. So these 2 things are opposites of each other. Light emitting diodes use electricity to make light. Photodiodes use light to make electricity, or to at least allow electricity to go through. Right? You either found that one in the book or you didn't. The good news for you guys is that there are no diodes on the upcoming test. Okay, you've done this sort of thing before. Question 6. 2 possible combinations of light globes in a 12-volt battery. Each globe is identical and has a rated power of 24 watts. All right. A, calculate the resistance of 1 light globe in circuit A. Circuit A. Let's have a look. 12 volts, which means because the electricity comes out here can go through 1 light or the other 1 light, but it won't go through both, the voltage across those is 12 volts. Across either of them. Right? Now it said the power of each light is rated at 24 watts. So for each light, power equals VI, which equals 24. So therefore, 24 equals 12 times I. That's got to be 2. The current going through each of those lights in this circuit would be 2 amps. So there must be 4 amps coming out of here, right? Because it splits so that these guys get 2 and those guys get 2. All right. That's part A, pretty fast. Part B, calculate the total resistance of the 2 light globes in circuit A. Now this is where you have to use that across here. That 1 over RT thing, right? This is parallel circuits. 1 over R1 plus 1 over R2. So, excuse me, what are we missing? We have to find the resistance first. Okay. So before we go there, we have to do this. V equals IR for one of these resistors, right? Therefore, R equals V divided by I, and we just got both of those for one of these resistors, right? The voltage, pardon me, voltage is 12, I is 2. 12 divided by 2, it's a 6 ohm resistor, right? So both of those lights are 6 ohm resistors. So let's get back to this. 1 over 6 plus 1 over 6, that's 2 over 6, and you have to flip 2 over 6, okay? Oh, I'm sorry. Got to watch the camera. 2 over 6. And you have to then flip that because that's 1 over R total. So therefore, the R total equals 6 over 2, which is 3 ohms. That's the total resistance in circuit A. All right. Question C, it's decided that one of these light combinations would be a useful circuit for car headlights. Which circuit A or B would be a useful circuit for car headlights? Explain your answer. Well, it would definitely be circuit A. They're wired in parallel. Couple of reasons. Firstly, because each light gets 12 volts here and each light gets 6 volts here because they have to share it, right? Loses 6, loses 6, loses 12, loses 12. These lights are going to glow brighter. For the same amount of electricity put in, these lights are going to glow brighter, right? For free. Secondly, if one of them breaks, the other one can still work. Right, because the other one still has its own dedicated circuit. So if that wire cuts or something and this light doesn't work, you're suddenly not driving through pitch black darkness. You've got one headlight still going. If one of these guys breaks, one of those guys breaks, the electricity can't get to the other one. Right? So both headlights are going to go out. Right? You hit a kangaroo on one of the headlights, and the other one's going to go out as well, and you can't drive the car until dawn. All right. Thirdly, although it's not really done in a car, you could switch each of these on individually. This is more important for houses, right? Those first two advantages are still good for houses, but also you could put a switch here and a switch there, and this switch only turns that one on, and this switch only turns that one on, right? So you can switch different lights in different rooms. Right? Here, one switch either has everything on or everything off. So parallel circuits have got three big advantages over series circuits. Question 7. This is a design for a simple circuit in a house. So these are lights here. Now they're in parallel so that each light can go on individually. You don't want to turn one switch on and every light goes on in the house. Right? So that might be a bedroom. That might be the ensuite. That might be a hallway. Right? Obviously they wouldn't be all lined up. They would be following the curvature and the design of the house's floor plan. But you get the idea. Right? Exactly what I said for the previous question. Each light has its own switch. And you're getting maximum brightness as well. So part A, it says explain why the circuit breaker, this thing, is on the active side of the lighting circuit. Now, if you've done your reading, right, the active part is where the electricity is going in, right? So there are three, seeing that, right? One of them's active, one of them's neutral, one of them's earth, A-N-E. I believe active is on the left when you're looking at it. Active is where the electricity comes in to the house. And then it has to go out. Keep in mind, this whole thing has to complete a circuit. So this comes all the way from the power station. It has to go into your house and it has to go out from your house and all the way back to the power station, or the circuit is broken and you don't get any electricity. Right? So there is always, right, at least two prongs to a plug. Some of them have a third, most of them have a third, but you have to have two, one for electricity to go in, one to go out. Now the reason the circuit breaker is on the active side is because the circuit breaker is to stop electricity going in if somebody is getting electrocuted. Right? If you have the circuit breaker over here, then somebody can still be getting electrocuted. For example, if somebody is touching this wire here, right, then electricity can still go in and into that person and then down that person's body to earth, and keep electrocuting that person. Right? If there's a breaker over here, it doesn't matter whether it's broken because that human being's body is making part of the circuit. You've got to stop it before it gets into the house. Right? Part B, explain the function of the circuit breaker found inside the fuse box. Well, I just told you. The circuit breaker detects if there is a difference in the amount of electricity going in and the amount of electricity going out. These two things are actually right next to each other in the circuit box of the home, right? They're not a room away. So the circuit breaker straddles across both of them. And if there's a difference between the electricity going in and the electricity going out, that means that some of the electricity going in isn't getting out because it's going through some human being and trying to kill them. And that's when it breaks the supply of electricity. So that the whole house goes off and this person is hopefully saved. Right? That's its part. That's its purpose. Excuse me. Explain why the 5 lights are wired in parallel. Well, I answered that question pretty much answering question 6. Firstly, maximum voltage going through, so they're all going to be bright. Secondly, they can all be switched on independently. Thirdly, if one of them breaks, the others can keep going. 3 big advantages to parallel wiring. Right? Part D. Do the light globes in this circuit have to be the same wattage? Explain your answer. Well, the answer is no. If they are different wattages, they'll glow for different brightnesses, and you want that. I mean, if you need brighter lights to light up an entire lounge room than you do to light up the toilet, for example. So they don't have to be the same wattage at all. You will end up, if you have different power ratings for each light, you'll just end up having different amounts of current going down each one of these. That's fine. They'll still take power of 240 volts. Sorry, they'll still take voltage of 240 volts. Some of them will end up sucking more power and glowing more brightly. Okay, part E says the circuit breaker is designed to trip when the current exceeds 10 amps, and initially there are 5 light globes and each have a 120 watt power rating. We've got to calculate the total current that's coming into the house to get all of those lights going. All right, so the total of all the light globes, right, the total power is 120 watts times 5, right? Excuse me, which is 600 watts. So 600 watts of power is being supplied to this house when all of these guys are on. Right? So power equals VI. Therefore, the current that's needed to provide 600 watts of power is going to be power divided by V, which is 600 watts divided by how many volts? It's a normal house, 240 volts. And that comes to, 2.5 amps. 2.5 amps of power is coming into the house in total to supply all of that light.